Hey everyone, welcome to this explainer. Today, we're tackling something that has, let's be honest, probably caused a few gray hairs for embedded devs everywhere. We're taking the notoriously frustrating, kind of intimidating STM32 clock tree, and we're going to completely transform it into an intuitive, logical plumbing system. If you've ever felt totally lost staring at hundreds of pages of microcontroller datasheets just trying to figure out why a single line of code won't run, well, you're in exactly the right place.
Okay, let's start with a completely universal frustration. We've all been there, right? You've written absolutely perfect code. The logic is flawless, the syntax is clean, you've checked it 3 times over. But when you actually flash it to your board, your peripheral silently does absolutely nothing. No compile errors, no runtime warnings, just total silence. It's exactly the kind of invisible bug that makes you want to chuck your expensive dev board straight out the window.
This perfectly highlights the absolute #1 beginner mistake in STM32 programming, trying to talk to a peripheral before enabling its clock in the RCC. It's a guaranteed fail. See, if that clock isn't on, the peripheral won't flag an error. It won't send a warning back to your debugger. It literally just ignores you. You're basically shouting into a void. So, let's look at our roadmap and see exactly how we're going to fix this hardware blind spot once and for all.
Here's our agenda for today's journey. First up, why clocks matter. Second, the 4 raw sources. Third, the PLL gear system. Fourth, routing power to peripherals. And finally, specialist clocks and troubleshooting. Basically, we're going to track the physical path of a clock signal from its absolute origin all the way down to a specific peripheral. All right, diving right into Section 1, why clocks matter, the heartbeat of your microcontroller. Why exactly is this the literal lifeblood of your chip?
The absolute crucial thing to grasp here is that the STM32 doesn't just have one single clock powering everything at once. No way. It actually uses an incredibly complex, highly segmented distribution network called the RCC, or Reset and Clock Control. Think of the RCC exactly like the main electrical panel in your house. Power comes in from the street, and a huge panel of circuit breakers decides exactly where that power goes. If the breaker to your kitchen is flipped off, your fridge simply isn't going to turn on, even if the rest of the house is lit up like a Christmas tree. In the STM32 architecture, if a peripheral's clock breaker in the RCC is switched off, that component is entirely dead to the world.
Now, what's really funny about looking at the full architecture is how absolutely terrifying it looks at first glance. What you're seeing is the complete STM32 RCC distribution network. And man, it genuinely looks like a subway map drawn by a mad scientist on their 3rd cup of coffee. It's just this massive web of lines, multiplexers, and logic gates. But hey, don't panic. By the end of this explainer, we're going to break this massive map down piece by piece. We'll trace the logic until every single line makes perfect, intuitive sense.
So, let's start at the very beginning of the maze. Section 2, the 4 raw sources, and where time actually begins.
Everything in that crazy clock tree starts from one of 4 raw sources. 2 are internal to the chip, and 2 require an external crystal oscillator. On the internal side, we've got the high-speed internal, or HSI. This is usually a 16 MHz internal oscillator. Now, it's not the most precise clock in the world. It fluctuates a bit with temperature, but because it needs absolutely zero external hardware, it's the ultra-safe default clock that fires up the literal second your chip gets power. Then, on the external side, there's the high-speed external, or HSE. This uses a physical external crystal, very often an 8 MHz one on boards like the Nucleo series, and it is highly accurate. Finally, on the slower side of things, we have the LSI serving the watchdog and the LSC driving the real-time clock.
Speaking of that LSC, or low-speed external clock, it typically uses a very standard, very specific frequency, 32,768 Hz. Now you might be wondering, why such a random-looking number? Well, it actually comes down to pure mathematical elegance in binary systems. See, 32,768 is exactly 2 to the power of 15. So if you take that electrical signal and divide it by 2 using a simple digital flip-flop, and you do that exactly 15 times in a row, you land precisely on 1 Hz, a flawless, zero-error, 1 tick per second clock. It's honestly just absolute hardware magic for keeping accurate time for years on end, all while running on a tiny coin cell battery.
Moving right along to Section 3, the PLL gear system. This is where we turn a slow crystal into a fast CPU clock, because let's face it, an 8 MHz crystal is way too slow to run a modern Cortex M4 CPU.
PLL stands for phase-locked loop.
To make this abstract electronic concept a bit more intuitive, imagine you're pedaling a bicycle at a slow, steady rhythm. That slow pedaling, that's your raw external crystal. The PLL is your bicycle's gear system. It takes that slow, steady input and mathematically multiplies it, making the back wheel spin incredibly fast. And at the exact same time, a second gear could split off to spin a smaller accessory at a totally different speed. The hardware PLL does exactly this, just with electrical frequencies instead of mechanical rotation.
Let's actually walk through how this builds step by step for a 100 MHz STM32 F411 Nucleo board, assuming we're starting from an 8 MHz external crystal. Step 1. The M divider slows our 8 MHz input down to a clean, stable 1 MHz. It does this because the core of the PLL actually prefers a slow, predictable reference. Step 2. The N multiplier takes that 1 MHz and multiplies it way up to 200 MHz inside the voltage-controlled oscillator. And finally, step 3, the P divider takes that massive 200 MHz signal and cuts it perfectly in half, giving us our flawless 100 MHz maximum system clock, which we call SYSCLK.
But here is a massive real-world quirk you absolutely have to watch out for when you're doing this math. 48. If your specific hardware project uses USB, the PLL output feeding that USB hardware, which is known as the PLLQ, must hit exactly 48 MHz. Not 47.9, exactly 48. USB hardware is incredibly strict with its timing tolerances. And if your internal multiplier is sitting at 200 MHz, like in our last example, well, there is literally no whole integer number you can divide 200 by to get exactly 48. So this completely forces you to backtrack and rework your entire math chain from scratch just to satisfy that one single USB peripheral.
Okay, so we've carefully crafted our fast system clock. Let's head into section 4, routing power to peripherals with muxes and buses.
Once our fully optimized signal leaves the PLL, it passes through the main system multiplexer and becomes the HSCLK. This is the ultra-fast heartbeat driving the main CPU core. But here's the thing. Most peripherals simply cannot handle that kind of raw speed. They don't sit on that main ultra-fast line. Instead, they sit on one of two advanced peripheral buses. APB1 is the low-speed bus. This handles slower peripherals like I2C and basic timers, maxing out at 50 MHz on our F411 chip. APB2 is the high-speed bus. It handles things like advanced motor control timers and extremely fast SPI communications, and that can handle up to 100 MHz. You have to be super careful configuring your hardware prescalers to ensure you don't accidentally fry a bus or cause erratic behavior by feeding it a clock signal that's way too fast for its hardware rating.
And this brings us to a huge plot twist, one that trips up nearly every single beginner learning this ecosystem, the timer doubling rule. Okay, pay really close attention here. If an advanced peripheral bus prescaler divides the main clock by literally any number greater than 1, the RCC hardware automatically steps in and doubles the clock fed specifically to the timers on that bus. So think about it. If you explicitly slow your APB1 bus down to 50 MHz, your I2C peripheral runs at 50 MHz, but your timers are secretly running at 100 MHz. If you calculate your precise PWM delays based on that 50 MHz bus speed, your physical timings are going to be off by exactly half. Always account for timer doubling.
Let's move into our final segment, Section 5, Specialist Clocks and Troubleshooting. We're going to look at fallbacks, built-in tools, and how to debug when things inevitably go wrong. A truly brilliant example of a specialist clock is the Independent Watchdog, or IWG. Its sole job in life is to physically reset the chip if your firmware gets stuck in an infinite loop or just crashes. Now, what's really fascinating about this is how it's powered. Think of it as a safety guard dog wearing a battery-powered collar. It completely bypasses the main PLL system and instead runs strictly on that slow, internal LSI clock we mentioned way earlier. Why? Because it's an incredibly clever failsafe. If your main crystal physically shatters or you mess up the PLL config and completely crash the main power distribution, well, the watchdog still has its own independent, untouchable heartbeat and can safely step in to reset the entire system.
Now for a pro-level debugging tip that is absolutely going to save you hours of pulling your hair out. If you suspect your clock configuration is wrong, use the MCO, or microcontroller clock output. The STM32 architecture actually lets you route your internal system clock, or a divided version of it, directly out to a physical pin on your circuit board. That means you can literally hook an external oscilloscope up to that specific pin and watch the raw square wave. It proves, without a shadow of a doubt, exactly what frequency your chip is actually running at in the physical world. It completely removes all the software guesswork and just tells you exactly what the hardware is doing.
So let's bring all of this together with a quick, definitive troubleshooting checklist.
If your peripheral is dead silent, you probably forgot the RSCA enable. If your delays are off by exactly half, you probably ignored the timer doubling rule. If your PC absolutely won't recognize your custom USB device, your PLL isn't hitting exactly 48 MHz. And if your code randomly acts unreliable or crashes immediately after turning on the PLL, well, you likely exceeded the strict maximum frequency limit on your APB1 or APB2 bus.
So I'm going to leave you with this final thought. The next time you sit down, you write absolutely perfect C code, you flash it to your board, but your SPI or UART silently fails, are you still going to assume the clock is running? By thoroughly understanding the RCC, you're no longer just writing software. You are actively architecting hardware logic. You're turning on the specific breakers, you're shifting the physical gears, and you're taking full, total control of the heartbeat of your microcontroller. Thanks for joining me on this explainer, and happy coding.